here's the interesting problem that I want to share with you. And it involves just taking the curve 1 divided by x, okay? And, since so many of us are musicians, let's say we're going to integrate this curve from 1, and, we'll just kind of roll this along like this, okay? And I want to find the area underneath this curve. But here's the deal. I want to do the area underneath this curve for a really, 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 really long time. So, instead of like stopping at 10 or stopping at, 20, I'm going to go all the way out to like, 1,000. Okay? All right, you okay with that? All right, now we know that this is the antiderivative, this is the natural logarithm, right? And in fact, we defined this to be, this is actually the definition of the natural logarithm, yes? So really, we can write the integral, but the answer to this problem all the way out here to 1,000 is that's going to be the ln of 1,000. So the ln of 1,000 is the exponent that you'd raise e to get the number 1,000, right? So can somebody pop that on their calculator really quick? And you know the ln of 1 is 0, so what's the ln of 1,000? You got that over there for me, Colin?
6.907.
Oh, I guess I probably knew that. Yeah. All right. So what do you think is going to happen if I change that 10,000, or that 1,000 to 10,000? Can somebody do the ln of 10,000 for me? Tell me what that is. 9.21. Okay. What's going to happen if I change that to 1,000,000? We're to 13 now? Okay. Is it going to keep getting larger forever and ever and ever and ever and ever? Yeah.
But it's going to be approaching 1.
Well, that's the question.
ln x doesn't have a horizontal asymptote.
That's right, it does not. It's slowly increasing, but it's always increasing. I mean, we just kind of convinced ourselves of that, right? Right? So theoretically, this is actually what we're talking about when we talk about an improper integral. So you might think, surprisingly enough, that if I just, do this based on this one little example that I have, you are right, we really need to think about the limit of this. And so I'm going to say the limit as b approaches infinity of the integral from 1 to b. Do you see how I, let b go to infinity here? And then we'll just evaluate this limit. We were just kind of evaluating it numerically. And we thought it was going to approach infinity. So ln of b minus ln of 1. And yeah, this is infinite because, as Greg said, this function doesn't have a horizontal asymptote and it's always increasing. So here's where I wanted to kind of blow your minds. And here's where the music connection comes in. If I rotate this region and create a solid, kind of like the bell of your trombone, or if we thought about like in medieval times, like when they would have those horns and they were like really long, right? Okay, so what would the volume of this be? Okay, so let's write a volume. You'll probably think, oh, it's infinite. Let's see. So let's do pi, right? And then that's going to be, let's just do from 1 to 10. And then I have to do 1 over x squared dx, right? Are you good? Okay. So, I mean, you can use your calculator to evaluate this. We could do it analytically, but maybe somebody can kind of set it up on the calculator while I do the algebraic antiderivative. Is everyone okay with that? And then you can just tell me what the answer is. So this is going to be x to the negative second when I rewrite it. So this is going to be pi times negative 1 divided by x. When I integrate this, and I want to evaluate this from 1 to 10, so this is going to be negative pi times 1/10 minus 1, and so that's going to end up equaling, that's negative 9/10, so that's going to be 9 pi tenths. And maybe somebody could check that on the calculator for me. Check my arithmetic. I don't think I made an arithmetic mistake. So then the question would be, what's going to happen if we change this to be, instead of 10, what if we change it to be 100, 1,000, 1,000,000, blah, 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 blah. So let's go, some of us are like, huh? Let's go slower. If I change this to 100, this is going to be 100, yes? This is going to become 1/100th, and so then this is going to be 99/100ths. Are you good? You good? And if I change this to 1,000, this is going to become 999 thousandths, yes? If I change it to 1,000,000 times pi, are you all right with this? So pi times the integral from 1 to 100 of 1 over x squared dx is going to be 99 pi hundredths. And if we just, keep going with this, we're going to get 999 pi thousandths, and, 99999 pi, and then that's going to be 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and as Alex just observed, that sequence of numbers is getting closer and closer to 1 pi, right? Do you agree with that? So it would appear that we have a weird little situation going on here where we have something that has an infinite area underneath the curve, and yet the solid that we create when we revolve it about the x-axis yields a solid whose volume is finite. And if we actually used the formula for the surface area of a region created by revolving, that was another section in chapter 8 that we didn't do, but we'll look at that after the AP exam. It's a good topic, it's just not an AP topic. It actually has an infinite surface area. So it's even crazier. This solid has an infinite surface area and a finite volume. Yeah, wrap your heads around that little weirdness. Now, could we set the same thing up like we did here and create a limit and prove using limits that this really is the way it is? Sure, let's do that. Let's take the limit as b approaches infinity of the integral from 1 to b of pi times x to the negative second dx. That's basically what we're looking at here. And that's going to be negative pi divided by x, limit as b approaches infinity. And this is going to go from 1 to b. And so we're going to get the limit as b approaches infinity of negative pi divided by b plus, right? Everybody okay with that? Plus pi divided by 1. Are we good? Are we good? Okay, so what's the limit of this term? A number divided by b as b goes to infinity, that limit is 0. So we end up with 0 plus pi, which is what we thought it was going to be when we looked at that numerically. Infinite area, finite volume. Crazy, crazy, crazy stuff. Okay? We used the technique of evaluating improper integrals to explore this problem right now. There are 3 cases in which you could have improper integrals. So that's what I want to put in your notes now. Oh, that actually would be a good idea. Thank you. You're so always thinking about me. That's so nice. So one case is when one limit is infinity. Okay, that's case 1. So that was what we just did here. Case 2 is when between a and b, the function is undefined. And then case 3 is the function is undefined at either a or b. So we just looked at a situation like this, 1 to infinity of 1 divided by x dx. That was what that integral would look like. And here's an example of this one. The integral from 0 to 3 of 1 over x minus 1 dx. So I think you can see that that function is undefined at 1, and 1 is on the interval from 0 to 3. And then the other case, we could actually just take this one here, and instead of going from 1 to infinity, why don't we go from 0 to 1? Nick?
These are only going to be definite integrals.
Yep, improper integrals are always a definite integral. Yeah. And sometimes there is a value, and sometimes there is not. Sometimes it's infinite, okay? And so basically the way you tell whether or not the improper integral has a numerical value is you set up a limit like we did earlier, and if the limit exists, that's the value of that indefinite integral, or that improper integral, excuse me. And if there isn't a limit that exists, then we say that that improper integral diverges. Okay? Uh-huh. That's right. That's when you would set up a limit to help you evaluate it. Probably the one that most frequently occurs on the AP exam is one where one of the limits of integration is infinity. The next most frequent one that occurs is where one of the endpoints limits of integration is a place where the function is undefined. This middle case here occurs less frequently on the AP exam, but it is also solved the same way. Okay? All right, so you're going to set up a limit in each case. And I'll just write these out. So this one would be the limit as b approaches infinity of the integral from 1 to b of 1 over x dx. That's easy enough. And if we want to come over here to do this one, we're going to take the limit this time as b approaches 0. And there's nothing special about using b, but most books that I see use b. And then so this would be from b to 1. See how we have to put the b in for the number we're getting rid of? Okay. And I think that one's going to be infinite because as we approach 0, the natural logarithm function is infinite. Okay. And then here, the way you have to set this one up is you have to, you actually have to use 2 limits. So we're going to use 2 letters. So we're going to do the limit as b approaches 1 and we're going to go from 0 to 1 of 1 over x minus 1, and then dx